Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I am going to solve GATE 2024 problems from the discipline of Electronics and Communication Engineering for the topic Network Analysis. So, Network Analysis is the subject common for Electrical, Electronics and Instrumentation Engineering. So, all those candidates can watch this video. Let me start solving the problems from GATE 2024. This is problem number 1 taken from easy paper. Easy means electronics. So here in the given circuit, I will read out the problem first. In the given circuit, the current Ix in milliamps is dash. So here one network is given. This network consists of two independent current source and one dependent voltage source. This 5 milliamps and 2 milliamps are the independent current sources, and here 1000 I naught representation is the independent voltage source. So we need to find the current Ix which is flowing through this 1 kilo ohms. Okay. So for solving this problem, we have two methods. We will solve one by one. First, I am going to solve by Kirchhoff's voltage law. So here 5 milliamps and 1 kilo ohms are in parallel condition. First, we can convert this current source into voltage source. So for the conversion, 5 milliamps in parallel with 1 kilo ohms. So by using Ohm's law, 5 into 1, that will become 5 volt. So circuit will be reduced like this. So 5 volt in series with 1 kilo ohms. Now we are having two loops. So I am taking Kirchhoff's voltage law only. I am taking this current as I1. Sorry, this current as I. I am taking first loop current as I only. And then second loop current is already given as Ix. So same Ix representation I am also assuming. Second loop current as Ix. So let me write the equation using Kirchhoff's voltage law. So by using Kirchhoff's voltage law, let me write the equation for two loops. For the first loop, by using Kirchhoff's voltage law, for the first loop I am taking the current as I. So we know Kirchhoff's voltage law is a sum of voltage drop equal to sum of voltage rise. So we are having two resistances, 1 kilo ohms, and in this branch also 1 kilo ohms. So for loop 1, I 1 into I plus 1 into I minus Ix, because second loop current is Ix. So the equation will be like this: I minus Ix plus I equal to voltage rise is two voltage sources are there. One is independent, other one is dependent. So 5 volt plus 1000 I naught. So we have written the equation for loop 1. And for loop 2, we are not having the voltage source. So here I minus Ix is nothing but 2 milliamps. So I have assumed the same direction only. Ix is the same direction only, and here in this middle branch we are having the current source value as 2 milliamps. So I have taken I minus Ix equal to 2 milliamps. Now we can substitute that I minus Ix in the first loop equation. So equation will be obtained as 2 plus I equal to 5 plus 1000 I naught. So I have taken this as first equation. And then for loop 2, I am writing the second equation. There is no voltage source. The total current is current in the loop 2 is Ix. So here 1 kilo ohms and here 1 kilo ohms. So we can write like Ix minus I plus Ix equal to 0. Okay. So here already we have taken I minus Ix equal to 2 milliamps. So Ix minus I means reverse of that, negative of that will become minus 2. So minus 2 plus Ix equal to 0. Therefore, from second equation, we can obtain directly the Ix equal to 2 milliamps. So this is one method to solve this problem. Let me solve by next method, that is nodal analysis. The same problem here I have solved by nodal analysis, because there are two independent source and one dependent source. If a network contains dependent source, it is better to take the nodal analysis method only. But for this problem, we have got the answer. But if any network is having any one even any one dependent source means we have to prefer for nodal analysis. So here, see here, we can consider this node as, we can consider this nodal voltage as V1 and this nodal voltage as V2. See here, between two nodes, there is one dependent source. If any source is connected between the two nodes means we can consider that as super node. We can consider that as super node. Okay, that is called as super node. So for the super node analysis equations, we have to consider only the current source. There is no need to consider that voltage source which is connected between the nodes. So irrespective of this voltage source, we can write the equation for the current at the two nodes. So this is first node and this is second node. I'm not considering this voltage source now. To write the equations, I'm not considering this voltage source now. So by considering this node, by super node analysis, this 5 milliamps is the incoming current. And here this is grounded voltage. So this is outgoing current. So V1 5 milliamps is the incoming current and V1 by 1 is the outgoing current. When considering the second node, this 2 milliamps is the outgoing current and for 1 kilo ohms it is to the grounded voltage, this is outgoing current. Now we can write the equation by not considering the voltage source, by not considering this 1000 I naught. So at least for current only we are writing the equations. So sum of incoming currents equal to sum of outgoing currents. So what are incoming currents? 5 and then 5 and what are incoming currents? 5. Okay, and then minus 2. So here we can write like V1 by 1 here for this branch and V2 by 1 for this branch equal to 5 is the incoming current, 2 is the outgoing current. So 5 minus 2 which is equal to 3. So we have written the equation. Thus simplifying that V1 plus V2 equal to 3. So I have taken this as first equation. And then we need to find Ix which is flowing through this 1 kilo ohms. Okay. V2 minus, can we write this V2 minus V1 difference of this nodal voltage equal to 1000 I naught. So we can write the equation like that. V2 minus V1 which is equal to 1000 I naught. So this I naught is nothing but current. I naught already represented here. Current flowing through this 1 kilo ohms. So we can write I naught equation as V1 by 1 using Ohm's law. Okay. Current flowing through this 1 kilo ohms is represented as I naught. So I naught is nothing but that nodal voltage by resistance. V by R. V1 by 1 kilo ohms is nothing but the I naught. Okay. I naught equal to V1 by 1. So like in the similar way we can write the equation for Ix also. This Ix which is flowing through this 1 kilo ohms, we can write equation using Ohm's law. V2 is the nodal voltage, 1 kilo ohms is the resistance. So V by R, by using V by R, we can write Ix equal to V by 1, sorry, V2 by 1. Okay, V2 by 1 kilo ohms. So we have to get V2 first. Okay, this nodal voltage. We have to obtain this nodal voltage. For that, V2 minus V1 equal to 1000 into I naught. So I naught is V1 by 1 kilo ohms. So for kilo ohms only 1 into 10 power 3 which is 1000. So 1000 into V1 by 1000, 1000 will get cancelled and then so we will get that as 1000 will get cancelled. So V2 minus V1 equal to V1, that will become V2 equal to V1 equal to V2 by 2. V1 equal to V2 by 2. Now by substituting that V1 in first equation to find V2, we have to find V2. So for that we have to eliminate V1. So that's why we have to substitute V1 equal to V2 by 2. So V2 by 2 is substituted in this equation to find V2. So thus we found 3V2 equal to 6 and then V2 equal to 6 by 3 which is equal to 2 volt. So we have obtained V2 equal to 2 volt. Now by substituting V2 equal to 2 in Ix formula, so Ix equal to 2 by 1, which is equal to 2 milliamps. Okay. So when a network consists of dependent source, it is better to consider the nodal analysis only. The nodal analysis is the best method to solve the problem. Okay. So let me move to the next problem. So this is problem number 2, taken from the topic oral circuit. First, I will read out the problem. In the circuit given below, the switch S was kept open for a sufficiently long time and is closed at time t equal to 0. The time constant in seconds of the circuit for t greater than 0 is. So at the initial condition, the switch S was kept open at the steady state condition. And after t equal to 0, the switch is closed and we need to find the time constant for t equal to 0 plus. Okay. So here one current source is given. To find the equivalent, to find the time constant, we need to find the L equivalent and R equivalent. So for that, we can open circuit that current source. If voltage source is given means we can short circuit to find the equivalent. So here current source is given. So we can open circuit the condition, open circuit the current source. By open circuiting the current source, so this branch will be discarded. Uh, we can find the L equivalent and R equivalent. So here only one inductance is there. So directly we can write L equivalent as 3 Henry. And then here 4 ohms and 4 ohms are in parallel condition in series with 2 ohms. So 4 ohms plus 4 ohms parallel with 4 ohms plus 2. This 2 ohms is in series with that parallel combination. So if two resistance are equal and it is in parallel condition means we can take half of its value. If three resistance are in parallel and are equal means we can take R by 3. So if here 4 ohms is a resistance that is equivalent and it is in parallel condition. So for the parallel combination we can write directly that is 4 by 2. So 4 by 2 is 2 plus 2 which is equal to 4 ohms. So now time constant. We need to obtain time constant. Time constant equal to the ratio of equivalent inductance to the equivalent resistance. So we can substitute the L equivalent and R equivalent 3 by 4 which is 0.75 seconds. Which is 0.75 seconds. Okay. So we got time constant as 0.75 seconds. So this is numerical answer type question. For the GATE examination, we are having 3 types of questions: MCQ, MSQ and NAT type of question. For MCQ only, there is negative marking. This is one of the NAT type question, numerical answer type question. We are having no options. So only we have to write the values. Okay. So here there is no negative marking for this numerical answer type question and MSQ type of question, multiple select type of question. In this type, there is no negative marking. So we can attend the question hopefully. So can we move to the next problem? Okay. It's problem number 3, taken from the network theorems. In the network shown below, maximum power is to be transferred to the load RL. The value of RL in ohms is dash. So this is taken from the topic maximum power transfer theorem. This network consists of one independent voltage source and one dependent voltage source which is represented by Vx. Okay. So here when a network consists of dependent voltage source, we cannot follow the normal method to find the Thevenin's resistance. Maximum power is to be transferred to the RL means we need to find the Thevenin's resistance. The maximum power is transferred when load resistance equal to Thevenin's resistance. So for this network, we need to find the Thevenin's resistance. For that, I am going to short circuit this voltage source because this is independent voltage source. We can short circuit that, and here we have to find out the open circuit voltage and Thevenin's resistance. So for that I am going to replace that load condition by voltage source. So here I have replaced that load condition, load resistance by voltage source, which in this voltage source is short circuited. Now we have to find the Thevenin's resistance. For that, I have taken this nodal voltage as V. Okay, this nodal voltage is V. We need to find this nodal voltage. This nodal voltage is nothing but like open circuit voltage or Thevenin's voltage. Okay, so here, and then total current is I. Okay, for that or Thevenin, we need to find voltage and total current I. So, when total current is passing through this branch, here one division and here another division is there. Okay. So, for RTH, we need to find the voltage and that current. For that, I am writing the equation by nodal voltage, nodal analysis. So, here I equal to incoming to the junction and here outgoing from the junction. Okay, here outgoing from the junction. So I am writing that V minus Vx here. V minus Vx by 2 for this branch. Okay, current for this branch is V minus Vx by 2. And then V by 5. 2 plus 3 is 5. V minus Vx plus by 2 plus V by 5 equal, that is taken as first equation. Okay, total current equal to current for this branch is V minus Vx by 2. Current for this branch is V by 5. Okay, and then by using voltage division rule. So here already they have represented across 3 ohms. Vx is the voltage. Vx is the voltage across the 3 ohms. So by using that, we can write the voltage equation as Vx equal to total voltage into that resistance by total resistance. So total voltage equal to, Vx equal to total voltage into that specific resistance by total resistance. So this equation has written by the voltage division rule. Now by substituting that Vx value in first equation, the equation is simplified as I equal to V minus 3V by 5 by 2 plus V by 5. Again it is simplified as I equal to 5 volt minus 3 volt by 10 plus V by 5. So by taking LCM as 10, this will become 2V plus 2V equal to 10I. So here directly we can find the ratio of voltage to the current. V by I. 4 volt equal to 4V equal to 10I. So thus we can find V by I equal to 10 by 4, which is 2.5. Okay. So we obtained the ratio of voltage to the current. So ratio of voltage to the current is nothing but Thevenin's resistance. So Thevenin's resistance is 2.5 ohms. We obtained 2.5 ohms as the Thevenin's resistance. So maximum power is transferred when RL equal to RTH. So when RL equal to 2.5 ohms, the maximum power will be transferred for the network. Okay. 2.5 ohms is the answer for this problem. Let me move to the fourth problem. It is taken from the two-port network. Okay. For the two-port network shown below, the value of the Y21 parameter in Siemens is dash. So here two port is given. We need to find Y21 parameter admittance. So Y21 admittance is nothing but the ratio of current at the output port to the voltage at the input port. I2 by V1. I2 by V1. Providing V2 equal to 0. At V2 equal to 0. So at V2 equal to 0 means voltage at the output port should be equal to 0. So for that, I am going to short circuit this second port. I am going to short circuit this second port. So now I am writing the equations. So here loop current is I2 and here I1 is flowing through this 4 ohms and I2 is also flowing in this direction. So we can write for this loop, first we can write the equation for the loop 1. equation for the loop 1. So here 4 ohms, 8V1 is a representation for the dependent voltage source. So for loop 1, we can write the equation for current flowing through this 4 ohms is I1 plus I2. I1 is flowing in this direction, I2 is flowing in the direction. So 4 into I1 plus I2 equal to nothing but 8V1 voltage rise. Okay, equal to 8V1. It is simplified as I1 plus I2 equal to 2V1. So I have written as first equation. And then I am taking the full loop. I am taking this as second loop. Okay, this is second loop. So for that, I am going to write the equation. For that, for the full loop, loop 2 is full loop. Directly, we can write V1 equal to 2I1. Okay, so here voltage equal to 2I1. Voltage equal to 2I1. Okay, voltage equal to 2I1, that is taken as second equation. Now substituting this V1 in the first equation, I1 plus I2 equal to 2 into 2I1, that is 4I1. 4I1 minus I1, we will get I2 equal to 3I1. Okay, I2 equal to 3I1. So what is Y21? It is the ratio of I2 to V1. So already we got V1 as 2I1 and I2 as 3I1. Now we can substitute in the formula Y21 equal to I2 by V1, which is equal to 3I1 by I1. This I1 gets cancelled and the value equal to 3 by 2. Value equal to 3 by 2, which is 1.5. The answer is 1.5 Siemens for this two-port network. Thus, we saw 4 problems from the electronics paper from GATE 2024 paper. Okay, so watch the video completely. Here, this is Mani's GATE Tech Vision. This is a channel for engineering lectures. You can view the lecture series and you can share the lecture series for your friends and relatives. Okay, this is very helpful for you. Subscribe to my channel. Thank you very much for watching the video. If any queries is there means you can mail to me. My mail ID is dmoneylecture@gmail.com. Thank you.